All right, thank you, Addie. And yeah, good afternoon, everybody. I'm Brandon Dotson from UCF. I'm just going to apologize in advance. I was definitely planning on clicking through all these builds, so apologies to Maria. But go ahead and click forward like 4 times and build out the slide you can. And while she's doing that, essentially, as we've heard this morning, right, before we land anything on a planetary body, that's all driven by modeling, and that modeling has to be driven by some form of equations, and those equations come from Plume experiments. And then the kind of underlying piece, if you go next, is that the geotechnical properties affect all of those things. And so that's really kind of what we're studying here. So if you go forward 2 slides, please. So when I talk about geotechnical properties, what I'm talking about are things like shear strength, cohesion, internal angle of friction, terms that are probably familiar to most folks here, but just a quick recap. So shear strength obviously is how much something can resist a shearing force. Cohesion is like the kind of inherent stickiness of a material when there's no load applied, and then they're related by this Moore Coulomb relationship, which is just a linear approximation that doesn't always hold for low gravity or normal load, but it works okay for this initial step. Let's go next, please. So we did a number of measurements initially to try to characterize a bunch of different simulants using just a small shear box where literally you fill it with simulant and then shear it and take measurements. Let's go forward 2, please. And basically what we found is that shear or cohesion actually varies exponentially with bulk density. And we did this for Lunar Highland simulant, Mare simulant, BP1, JSC1, all the classics. And if you go forward one more, we see that that actually falls pretty well within the range of measured values from Apollo Surveyor and then the Russians with Luna. Let's go forward like 4 and let's see where that lands us. All right, so we've done a number of experiments now applying those same geotechnical measurements, both in atmosphere, cold temperature, and some vacuum stuff. Let's go next. We'll talk about atmosphere testing. So what this looks like for us, you can go next, is basically we have that same setup that Phil showed this morning with a acrylic split plate and a pipe with compressed air. We fill it with simulant and watch the fun. Let's go next. But before we do that, we actually took some measurements using a small pitot tube and some translation stages. So we really understood what the plume was doing. And in this case, we're getting Reynolds numbers on the order of like 30 to 40,000. So definitely well above the threshold into the turbulent regime. And really with exit velocities around like 55 meters per second. Let's go forward 2. And so while this is playing, basically, this is what it looks like when you do it. What we do is we try to measure the density very closely and vary it very closely. And then you can go ahead and click forward like 4 and build that slide out. So that gives us, basically, we track those edges over time and we can fit it with a logarithm like this with those fit parameters. Let's go next. And these fit parameters, you can continue to build this. Phil has put together, you heard this morning, some relations of how those fit together to help estimate the erosion rate. And really for this complex crater shape, using the collapse of the outer crater. Let's go forward 2. It's kind of brutal, it's good. He also came up with the idea, as he mentioned this morning, about the relationship between kinetic potential energies and cohesive energy density. Let's go forward 2. And so from those experiments, right, you saw this equation this morning. I've changed some of the constants here to try to keep them equal, but those are really the equations that we're probing here with these experiments. So let's see how they stack up. Let's go forward 3. Keep going. There we go. Okay, so right off the bat, we see when you use cohesionless soils like glass beads, like these 40 to 80 micron glass beads on the left, you do get that kind of unique complex shape. On the right, though, when you use more cohesive things like Lunar Mare simulant or Highland simulant, you get a very different shape, which means there's some sort of equation, if you go next, that we don't know yet. How does that change when you have a different shape like that? And where does that boundary exist between different levels of cohesion? So let's go forward 3. So as we do that, one way to get around it is to instead just fit this steady state crater development part using a linear fit. And then we'll go next, and I'll show you what some of that data looks like when we do it like that. Next slide. Okay, so this is what some of the volumetric erosion looks like versus sample bulk density. And this is for a whole host of different simulants that we're showing here. And the different colors represent mass flow, with the highest line being higher mass flow. So this plot is kind of weird. It didn't seem right at first, and you see larger difference on erosion rate with density for higher mass flows. And the bottom two lines are kind of squished together. So what we try to do is then divide everything by essentially that kinetic energy or rho v squared term. That should make it pop out a little bit more. So let's go next. That's what that'll show. And when we do that, we find it does generally fall along this line. It's not a perfect fit. These tests are definitely in the turbulent region and hard to see. But what we see from this, if you go next, is that density does seem to vary inversely proportional to, erosion rate is inversely proportional to density. Let's go next. So how about cohesion? So we take those same values I showed earlier in the brief and we plot them now against mass erosion. As you remember, that plot before had density in it, so we don't want to double count density, but so showing it against mass. What we see is this kind of makes sense for higher mass flow rates, we really don't see cohesion having as big of an impact. And for lower ones, we see a decreasing erosion when the cohesion goes up, and then it generally levels off at some value. Let's go next. So that does, again, kind of show us that we're on the right track here with its 1 over rho, rho being the density of the soil, and then cohesion. Let's go next. All right, so then here I've plotted essentially what that equation looks like against the data. You can see it generally falls kind of close to this line, which is pretty good. So let's go forward a couple of clicks here. And what we see is that equation actually looks kind of good, the one on the right here. But we really don't know what this value k is. So let's skip forward like 3 or 4. We think maybe it's related to the thermal velocity. So we did a bunch of cold testing here at Honeybee Robotics at minus 10 degrees C. And you can keep going forward here until you get to the plot. And here's what some of that early data looks like. What we see is that there is like an order of magnitude decrease in the rate of erosion when you go from room temperature to minus 10 degrees C. And that's definitely weird. We didn't expect that. If it's thermal velocity, it should be relatively small. We've got a couple theories in the works here of why we might be seeing that, but stay tuned for how that flushes out. And let's skip forward, I don't know, until you see vacuum testing at the top. Skip all this. All right, so getting short on time with all the skipping around, so I at least wanted to let you know we just finished up a 4-week campaign out at Honeybee again using their 3 cubic meter vacuum chamber, doing these same plume measurements. We looked at a couple different heights of the nozzle. In this case, we're just using a straight pipe. And if you go next, show you some of the ranges that we looked at. We basically stepped through a number of different ambient pressures from essentially 2 millitorr all the way up to ambient. And you can see we're pretty well nested with the previous test done out of Marshall. But let's go next and I'll show you just some quick teaser trailers. We are seeing, it might be kind of hard to see in this picture, but down in the lower pressures, so like 2 millitorr, you do see streaking, just like you see on the right here during some of the Apollo landings. Let's go next. We also see definitely some weird patterns that develop from shock interaction with both the walls and the surface and the flow itself. And next. But basically, stay tuned. We found something pretty interesting, but we definitely want to make sure it's a real thing before we present it to the wider community. And then let's go ahead to the conclusions here now that we're on time. So yeah, that initial approximation, it works pretty well for cohesionless material like glass beads, but we need to kind of rethink that for materials with cohesion. We think this term, this equation that Phil came up with is actually a pretty good one. Still trying to figure out what K is. And C does seem to be related in some form to cohesion. So with that, I'll go ahead and wrap up there. Thank you for your time.
All right, yeah, thank you, Brandon. Let's see, I don't think we have a reminder that y'all can put questions in on the IO tool if you have any for the speaker. really interesting talk, and I feel like I've got a question formulating that I wasn't quite certain how to ask, but I'm interested in sort of the correlations that you showed, and thinking about the correlations between the variables that you're testing, but also can you kind of comment on that in light of uh, the different crater shapes that you're observing, and thoughts about whether or not you might see differences, or what relation do you think that might have to crater geometry, or sort of varying geotechnical properties? Do you think you'll see sort of consistency there, or how might that affect those results?
Yeah, so I think just going off the cuff here, I think the dominant features that sort of drive crater geometry are things like ambient pressure and your nozzle mass flow, what that looks like. The geotechnical, it seems to really rear its head when things are down in like the lower mass flow range, but that's not to say that they're not important. I mean, we definitely see a lot of material, particularly at high densities, even under vacuum conditions, that will um, be excavated. So it's something it's like you don't care about it until you do, right? I think is kind of the point, is to show that, like, yeah, there's some importance to considering density and cohesion in these equations.
Okay. All right. Yeah. Thank you, Brandon.